Hey everybody, it's Mr. Carr again. We're going to talk about 8.2, what's called special right triangles. So we're going to keep going with our right triangle idea, and we're going to be talking about them in these two special cases. One is called a 45-45-90 triangle, and another is a 30-60-90 triangle. Okay, so the idea is this. If I have and really what it is it's an isosceles right triangle, then what I have is 45, 45, 90. Okay, so that's another name here. It's an isosceles right triangle. We get a certain pattern for the sides. And there's two ways to look at this. And when I go through some of the examples, you see how you can use either method. One method is that I'm going to call each of these sides, if I have an isosceles triangle, they're both going to be called x. Okay, so when I look at that, they're both just x's there. My hypotenuse ends up being x times the square root of 2. It's always going to follow this pattern. So whatever these sides are. So for example, let's say this side is 3. That means that this side is also 3, and this is 3 root 2. So that's one way to think of these types of problems. You just follow this pattern. X, x, and x root 2, it just follows that. You get a little bit tricky if I give you a number here. So let's say the hypotenuse is 5 root 2. That one's not bad. If I follow the patterns, this will be 5 and 5. Again, just following that pattern. So that's something that is true for 45, 45, 90 triangles. 30, 60, 90 triangles. So we got 30, 60, okay, and then the 90. So they have a different pattern, but they still follow the same thing. So across from the 30. So here's one thing to remember with triangles. The smaller the angle, the smaller the side that's across. So that's my smallest side there. We're going to call that x. When I compare the hypotenuse, in this scenario, it's actually double the size. So in this kind of a right triangle, the smallest side is x, the hypotenuse is double that. The third side, that last leg there, across the 60 degrees, is going to be it's a middle spot. It is x times the square root of 3. Okay, and you might think that, oh, well, it's 3 in there. That's the longest side. No, it's not. Compare 2 to the square root of 3. Square root of 3 is actually smaller because 2 is the same as square root of 4, right? If I had square root of 4 there, you could say, oh yeah, root 4 is bigger than root 3. Okay, so that means this is actually the longest side for hypotenuse, 2x. So remember, x is across here, x root 3 is across from there, and then 2x is the longest side. Again, pattern-wise, you can just do this. If I say, oh, that side's 4, my hypotenuse is going to be 8 because I double that, and then this is 4 root 3. Okay? Now, the other method here is to remember that what we're dealing with in this unit is similar right triangles. So another way of kind of thinking of these two types of problems is this. Every 45, 45, 90 triangle is similar to this triangle. And remember what it means to be similar, it means that it's proportional. So what I'm looking at here is if I can line up these corresponding sides, I can just write them out in proportions. Okay, I'm going to show both methods. I'm going to show both methods here in just a little bit, but I want you basically to choose what's best for you, what makes the most sense to you. Same thing over here. If I look at a 30, 60, 90, oops. Okay, so 30, 60, 90. So across the 30, I'm going to call it 1. I'm going to double that over here for 2, and root 3 is that leg. So again, you can set up ratios and proportions for all these things. All right. So here's a scenario. What are the lengths of the legs of this triangle? I don't have any angle measurements, but I do have this. Just like I said, isosceles, right triangle. It's going to be a 45, 45, 90. So here's what I can do. First option I'm going to do is I'm going to do the x root 2 idea. So something to kind of mention as well, you notice that these two match up. If I go from x to this way, I would multiply by root 2. That's the easy way to get there. So what's the pattern to go the other way? How do I go from x root 2 to x? Well, if I'm multiplying by root 2, if I reverse this order here, okay, when I turn this into this, I'm going to divide by root 2. That's a way to think of this. As terms of patterns, to turn x root 2 into x, I'm just going to divide by root 2. So that's what this is. If I want to turn this into the sides, I'm going to divide by root 2. That's one way to do this problem. So that means I'll say leg is x. It'll be root 72 over root 2. Here's a property of our radicals. If I divide both by the square root, it's the same as doing this. It's the same as the square root of 72 over 2, which is going to be the square root of 36, which is 6. So there's my answer there, 6 and 6 for my 2 legs. Now, the other option here is, like I said, to use this as a base triangle and do a similarity thing. Root 72 and root 2 are both across the right angle. So what I would do is this. Option 2 here is I would take, let's say my base triangle is 1, and I want to put it over x. My base triangle is root 2, and then square root of 72 is my other. Like I'm basically, what I'm doing is I'm comparing this leg to that leg, that hypotenuse to that hypotenuse. Okay, I'm setting up a proportion here. When I have my proportion, I'm just going to cross multiply. So then I get x root 2 equals the square root of 72. Divide by root 2. And I get, oh, look at what I have here. It's the same exact math as earlier. It's going to be the square root of 72 over 2, which is square root of 36, which is 6. Either way will get you the right answer. It's just how you prefer to look at it. Do you want to just focus on the pattern? Like if I look at here, this gets multiplied by root 2 to go that way. It gets divided by root 2 to go the other way. And then these are just matching up. Same thing here. If I go from x to 2x, I'm doubling that. Here I would divide by 2. Here I'd multiply by root 3. If I go this way, it's divided by root 3. Okay? That's the idea. So we'll do another one here. So what are the angles of the triangle? All right, so the question is, does this follow one of my other patterns? Well, I'm going to take a wild guess that if we got this angle not matching up to that one, it's probably a 30, 60, 90. But let's double check. We've got 8 and 4 here, okay? So yes, this is in the kind of x and 2x position. Question is this the same as x root 3? Well, here's what I can do. I can just honestly just confirm it in a calculator, okay? This should be 4 root 3 here. But is 4 root 3 the same as square root of 48? Well, I can break that down. This is what I'm kind of referring to earlier. The square root of 48 can be broken down into smaller pieces. Okay, this is actually from the previous lesson when I talked about the idea of exact versus approximate. Okay, so if I look at square root of 48, we're going to look at what multiplies 48. Well, 4 times 12. 4 is the same as 2 times 2. And then 12 is 4 times 3. And then 4 breaks down, and 2s and 3s do not. So I have 2 times 2 times 2 times 2 times 3. Remember, when this is in the radical 48 like this, every level is technically still inside the radical. So what I really want to start looking for are pairs. The reason why? What's the square root of 2 times 2? I get most students to say, oh, it's square root of 4. True. And then you evaluate the square root of 4, it's 2. Well, shortcut. If I have a number, the square root of a number times itself, it's just a number. Like I don't have to do this middle step. I could just jump right here. I'm going to do the same thing here in my factor tree. Since this is technically the square root of 2 times 2, that means I'm going to have a 2 on the outside of the radical. Here I have another 2 on the outside of the radical, and those 2's will be multiplied together. And there I have a lonesome little 3 who stays on the inside. It's a buddy system. Can't leave the radical until you have a buddy. So I have 2 times 2 is 4, radical 3. This is the idea that this isn't my exact number. If I did the decimal, which would be about 6 point, I don't know, probably about like 9.5-ish, that's the approximate. So what I just confirmed is that I do have, with root 48, that is equal to 4 root 3. So if I go back to my reference triangles up here, the across the 30 is my smallest side is 4. Okay, so this is going to be my 30 degrees. This is obviously 90, leaving that 6 or 60. Okay, and that's it. We're just kind of working backwards a little bit there. Just because these get a little bit tricky, we'll go ahead and do these other 3 you try nows as well. All right, triangle has sides that measure 2, 2, 3, and 4. What special right triangle has these sides? Again, you're just going back. We've got 2 and 4. If I were to try that, draw that out, I've got a 2 and a 4. 4 is the longest side, so that's going to be double the short side, and then 2 root 3. Okay, when I have this scenario, that's my 30 degrees, that's my 60 degrees. So I have a 30, 60, 90 triangle. That's just recognizing the patterns that we have going on. One leg of an isosceles right triangle measures 1 unit. Isosceles right. So I'll draw that out. Isosceles right triangle. One leg measures 1 unit. What is the exact length of the hypotenuse? So remember what we did before? This isosceles right here. I'm actually already done because I have 1, 1, and root 2. So the exact length of the hypotenuse is root 2. Again, leave it as a square root of 2, not the decimal number, which would be like 1.4 something. All right, final one here. The leg opposite the 30-degree angle. So I've got a 30, 60, 90. Draw it out. Okay, the leg opposite that has a length of 5. What is the length of hypotenuse? Once again, I don't care how you want to do it. You want to do, I'll set this one up as a proportion here. So across the 30 is 5. Across the 30, up here, there we go. Across the 30 here is 1. So 1 and 5 are corresponding. The hypotenuse is 2. The hypotenuse down here is unknown. So my reference, I'm going to just draw that again. It's 30, that's 1, 2, and then root 3. So if I do this as a proportion, I can do 1 over 5, 2 over x. Now you might have a shortcut on this one. Use it. I'm just showing you that I can do proportions here to solve. So cross multiply. I get x times 1, 2 times 5, x equals 10. And that's the length of my hypotenuse now. Okay, 30, 60, 90, and 45, 45, 90 triangles just take a lot of practice. You just got to get used to it and looking for those patterns, okay? You're looking for whatever works best for you on this one. If you come up with a different option that you think works, check with me. There might be one that works pretty well, and I just want to make sure of it before I commit that, say, yes, use this other method as much as you want. Okay, so just check with me real quick if you feel like you come up with a different pattern. All right, that's it for 8.2. I will talk to everybody later. Take care.